In the previous notebook, we introduced Marimo and we demonstrated some of its core capabilities. We also saw how we could use Marimo and DuckDB to process the output from volatility plugins. So the way we did this was to use the Parquet renderer and load that data into a DuckDB table. The only problem with that was we were forced to use SQL to write our queries. And this is why in this notebook, we are introducing the ibis data frame library. So what ibis is a data frame library that supports multiple backends. So it looks very similar to Polars or Pandas in that you're using a Python data frame syntax, like for example like this, to build up a query. So behind the scenes, ibis is actually creating an intermediate representation of the query. And then you can connect ibis to Snowflake, to Postgres, to Spark or DuckDB. And when you execute the data frame operation, it will emit SQL code for that particular backend. So if you connect it to Snowflake, you will get the Snowflake SQL dialect, or if you connect it to DuckDB, you will get the DuckDB SQL dialect. So basically what happens is you can write this code, and then when you execute it on DuckDB, it will actually execute this query, which solves the issue. Some of you might wonder, why can you do all this in Polars instead? And that is true. You can do everything in the workshop just by using Polars. And in some ways, it's a better fit for just the sort of forensics use case. However, the great thing about ibis is that it supports multiple backends. So increasingly, you store the your security data. So I'm talking about EDR logs, firewall logs, NetFlow logs, and so on. Not necessarily in SIM or Elasticsearch, but maybe in a system such as Snowflake or Databricks. That means that you can use ibis for querying these systems using the same data frame API that you use to query the forensics data. So you could perform one query in a notebook where you process, say, the DLLs listed from for the processes in the memory dump, and then you can have another query that used information from the EDR logs that were contained in, say, Snowflake or Panther. Okay, so I've opened up an empty notebook here to just demonstrate how ibis works. So let's get started by first importing ibis like this. Okay, so we got ibis loaded. Now let's just use the default backend DuckDB to read the output from the PS list volatility plugin. Let's just store the result of read parquet in the variable t. Okay, so let's see what we get. So we didn't get a table back this time. We got this display, which shows us what is this is a representation of the query. So what actually happens is that ibis by default is executed lazily. So it doesn't actually perform the query before you explicitly ask it to do it. So this is just a representation of the query, and then you have another tab here which shows us, how this would look in DuckDB. So to make this more clear, let's do like a select operation where we try to just extract the PID and the handles. So we are reading the data like this, and then we get a table representation consisting of these columns, and then we do a select operations where we extract just the PID and the handles column. So again, you can see here that the query plan or query representation has been expanded upon. So what happens is like this is the first part of the query. Like we read the table using read parquet, and this is a schema of the table, and then we use a project operator. So that is the select statement to extract PID handles from this table expression above. And now we can see something that looks very familiar. So if you actually want to look at the data, we need to force it to execute the query. So there's a few ways to do this. You can call the execute method like this, and what happens is that it will execute the query and return the results as a pandas data frame. And now we can see that we actually get the data frame back. So if we were to do this query here, let me copy it down, and then I do execute at the end of it, you can see what we get a data frame back with just two columns, the PID and the handles columns. The other option is to use 2PyArrow, which converts the result to a PyArrow table. So it looks pretty similar because Marimo has also built-in support for PyArrow tables. Or you could convert result to a polars table. So it's similar to what we did with the DuckDB query, where you chose the output format. Like this, two polars. Let's head back to our companion notebook. So here we have here we are reading the processes, and then we are converting it to a polars data frame, and then it's rendered by Marimo as a table. So this is the same table UI which we used in the DuckDB in the previous notebook. So this actually has a lot of features. So to demonstrate some of these, if you click on search here, you can actually do, or I've already done it, but you can do some free text searches. So this will filter out any rows that do not contain the value command.exe in any of its columns. And then you have the chart builder, which we used before to create our Altair chart of the process creation bar charts. And then you have the row viewer. So again, this is an interactive component. So if you click on a row, this will update. So we can then see the column values for that particular row displayed here, which is kind of useful if the contents of a row is like some larger text or like some HTML or bytes or something. Then you have the column explorer, which is very similar, which shows you some statistics about the column. So if you do image file view here, you can show you displayed all the top 10 most common file names. So this is similar to what we had in the data source panel here. And then you can also do search for the column names like this. PID. So it has actually a few more features. So for instance, if you click here, you can do again text search for that particular row. You see you get like some type of query here. Image file name should contain command.exe. And then you can do filter by value. So you can say, I just want to look at the rows that contain this one or this one or this one, or just like these two, and apply this. And then you can see here in the column explorer that this is actually updated. So this is the interactive component of Marimo. So all these things are connected. So you have this. You have also the ability to do like ascending or descending sort. And then you can use this to kind of like format the table for instance, if you do like, I want to actually freeze this column, I want to freeze this column, I want to freeze this column. So you can customize your display. You can also do like, actually I want to, let's see if I can format this in a meaningful way. Actually, that was kind of difficult because the offset should be represented as a hex, but let's just try a different format here. So it's going to look weird, but yeah, something like this. Can we do like a format here as well? Format this as, let's see, time, I guess, like this. You can format it as something like date. Let's see if we can format this as well. Yes, no. So you can apply, there's some built-in formatting options. In the next notebook, we will really go deep into this because the table widget, you can customize it a lot and it's really powerful. But for now, we have a few exercises. So we want you to get hands-on experience on just working with the output using the table widgets. So you have exercise 1, Exercise 2. ibis by default uses what's called deferred execution. So it builds up this query plan using this intermediate representation, and you need to trigger the execution yourself, either by explicitly calling execute or to polars or to pandas or something like that, or by writing to a destination. However, you can enable eager execution by enabling what's called interactive mode. So the way you do this, let's go back to this scratchpad, is you access the options of ibis and then you set the interactive attribute to true. So if we take this query here again, or you could just rerun, let's just rerun this query. You see that now we didn't have to call to execute or anything. It just somehow was automatically executed. So what we're going to do moving forward is, if we what we want to do is, let's remove this again. Let's remove this, and what we want to do is, just have it be at the start like this, and then we should just re-execute this. You can see, okay, now we're kind of good to go. We can continue and we can do like, hey, let me look at the data like this. Actually, I want the handles as well, like how many are there, and so on. Okay, so this is where we're at now. We have enabled eager execution, and we have connected ibis to DuckDB, and we're able to read the parquet file, so the output from the volatility plugin, into memory. And what do we do now? So there's really two things we can do, and that's doing table operations and column operations. So the table operations are like filtering, selecting columns, adding or changing columns, doing like order by, group by, or joining different tables together. So let's just demonstrate some of these. So okay, here we have interactive mode enabled. We have the first operation is just to get the parquet file into memory, and then we can start writing. So we can do pid handles like before, for example, or we could do like t filter. Let's say what we want to do. We need to do image file name like this equals command.exe like this. So that's a filter operation. What more do we have to look at? Let's say we have the table, and we actually want to create a new column called file name, for instance, like we do like this, file name. Then we need to refer to the existing file name column like this. And then actually just let's chain this together to extract just this new column. Okay. Let's see what else, join, mutate, and so on. We will revisit some of these later below. And yeah. Now the column operations, they work on the column values themselves, right? For example, let's go back to this, and then we do a select operation, and we want to, for instance, change this to be lowercase. So we can call to lower like this, and you can see that we have actually transformed this. We created a new column called lowercase image file name, and then everything is lowercase. We can, to make this more pretty, we can do like this. Actually rename the column to be called image. We've taken the original column values and performed and changed it to be lowercase. Okay, so what I think we should do now is go through some of the more commonly used table operations. So we have one section for each of these. For example, filter, that lets you keep the rows that match a Boolean condition. So this is same as the where clause in SQL. So you have the filter method here, and you pass it a Boolean expression. In this case, we want to so like retain only the records for which the PID is less than 1,000. And then these are ibis's Boolean expression type. So you can chain these together using and or by passing multiple conditions to the filter method, like so. Or you can also pass a list of elements. In this case, we are removing every row which doesn't contain a PID less than 1,000 and doesn't have threads greater than 5. So you can see here the PID is 4 and it has 156 threads. This is something I want to highlight now is if you're ever curious of like what is going on when you could create like a complex query, you sort of chain together these table operations. You do like some filtering, you select, you do an order by and a group by and joining together things, and you're sort of thinking, hey, what is actually going under the hood here? Then you can inspect what is sent to DuckDB by calling ibis's toSQL function. So it takes a table expression like this, and then it returns the actual SQL statement. So in this case, we pass this table expression with the filtering operation we just talked about. And in this case, you see, okay, it's a select statement where you read from some weirdly named table, and then you have this where clause, which does the filtering. I should mention that the reason where does this come from? So this table is actually created by ibis's read parquet function. So what happens is that when you read when you read a parquet file, ibis will create a table, DuckDB table, in a sort of temporary catalog, and the name of the table will be ibis _ read parquet and then some random string. If you specify the table name as an argument to read parquet, you won't get this. Okay, let's continue to the next operation, which is very familiar. It's the selection of columns. So in this case, as we saw before, we have the process table. We want to select just the PID, the image file name, threads, and handles. You can pass it strings like this, or you can use the column objects directly. Like so, you have the process table, and you pass it processes.pid, processes.image file name, and processes.threads. So this is pretty familiar. Feel free to do this exercise before moving on. Okay, now we have the drop operation, which is exactly as it says. It drops the columns you don't want to retain. In this case, we want to drop all create time, exit time, handles, file output. You see it's not part of the resulting data frame or table expression. Then you have mutate, and that creates new columns either from existing columns. So for example, here we are creating a new column called image _ file _ name, which is actually just the original image file name column, but we perform a column operation that lowers that converts every character to a lowercase one. So we can also pass in literal values, so that would be things that aren't from an existing data frame, like just a number or a string or something like this. And in this case, this was a bit weirdly formatted. Let's clean this a bit up. Yeah, what's going on here? If you clean this up a bit, it's easier to see. Yeah, you can see that we are calling mutate, and then we're creating a new column called analysis date, which is populated with datetime now, and then we have another new column called analyst name, which is the string Erica. So I think if we go to the very end, you can see, okay, fine. We have added 2 columns. So yeah, feel free to do this exercise. Now order by, this is just sorting. So the default is to sort in ascending order. You pass it the column that you want to sort by. In this case, processes threads, and then you actually need to call .desc to get the descending order. You can use multiple columns by passing them like this in the order that you want to use them. You see here I actually perform a column operation. Okay, so the real way to use ibis is to do method chaining. So what that means is that you first do one operation and then you call a method on the result of that operation, like this. So you first do select, and then you filter, then you order by, and you rename. So if we go back to this, and we'll actually need to define like a new variable like this, just so to get the names lined up. Okay, so first we do the selection operation, which returns a table expression. Then we call the filter method on the result, so on the table expression that was created here. And then we call order by on this table expression, and then we call rename on this table expression. So if we execute that, we see that we are missing an import, which we can fix from datetime, import datetime, like this, which is what we want. And then we can comment out some stuff. We can also, as we see here, we could do it in steps. So we can do sort of like, we can do like the first two steps as one expression that we store in a sort of auxiliary temporary variable. Let's call it new processes or something like that. Okay. And then we can continue to work with it by doing the remainder of the operations like this. New processes. Let's just get rid of this. So you can do it step by step. You do like a huge chaining operation, or you can split it up into these auxiliary variables. So you have to keep in mind that the default mode is actually deferred execution. So nothing would happen like until the very end. Like, so you can have functions that take a table expression and do some operations and then return another table expression, and then you can continue working like this until the very end. So these expressions can be quite verbose if you don't call your tables like T or something short. So in order to help with this, ibis has this underscored API, the deferred API. So if you import this symbol, underscore, like this, what happens is that if you use that in a table expression or column expression or something like that, it will evaluate to self, basically. That's how you should think of it. Like, it's sort of the current method, the current table. So let's say you have the T table again, and you do this. So what happens here is that the underscore will behind the scenes evaluate to T, like this. So it's the same as this. Now this is super useful when you do these huge chaining operations. Like, just let's go back and take this example again, like this, and just execute this. So what you can do here is you can actually use this instead. For example, here, instead of processes, you can do this, and instead of processes, you could do this, which makes everything really shorthand and concise. So going forward, we will use the deferred API as much as possible. Sometimes if you're doing joins or something like this, ibis won't be able to figure out what the underscore refers to, which table, and then you have to be more explicit. But usually it works. Okay, so since the deferred API and the method chaining is really core to ibis, please experiment with this and go through exercise 7. Okay, so we have introduced the deferred API, and you hopefully have mastered method chaining. So we can now move on to group by and aggregate. So the group by operation, what it does, it's allows you to group together rows that share one or more column values. For example, let's say you have the processes data set and you want to group together all the processes who have the same file name. So this will create groups for command.exe, notepad.exe, and so on. And then what you want to do is to feed the result, so all the groups, into a set of aggregation functions. Right? For each group, you want to perform an aggregation function. And that could be simple as, okay, group together all processes with the same image file name, and then count the number of rows in that particular group. So the result of this query, you can see you have 55 unique image file names, and then you can see that most of these are the most common one is svchost.exe, firefox.exe, command.exe, and so on. You can also perform additional operation on these groups, which we encourage you to read about. And you also have a bunch of shorthand methods of working with groups. And these are just more like syntactic sugar that it's useful to know about. One trick here is, like you can see, you can use the deferred API to create a Boolean condition outside of the table operations themselves, which could be convenient to make your query more simple or readable. So yeah, again, go through this section, read the documentation, and work through this exercise. Group by is kind of like a foundational operation that it's useful to master. Yeah, exercise 9, and then we proceed to the joins. Okay, so far we've only worked with a single volatility plugin, or actually we also use the DLL list plugin in the Marimo notebook. But let's say you have the process output and you want to combine that with the output from the NetScan output to see what network connections were present in the memory dump for each of the processes. So that's where join come in. Like you have two tables and you want to join them together based on a common value. So for example, if you have the processes that contain a PID and you have the network connections that also contain a column with a PID, you do a join operation that sort of create a new row that contains the rows from both of these tables. So yeah, here we are again, just calling readParquet to read the NetScan plugin data. You can see how it looks. And then we have the process table expression from before. We use the join method, pass in the table expression that we want to join with, and then we pass in the name of the column that we use sort of to match the rows from the two tables. And then we can see that the resulting table contains everything from processes together with everything from the NetScan. So the NetScan and processes join operation wasn't super interesting because most of the columns were already present in processes. So we have another example here that shows two different volatility plugins. So we have the one containing the security privileges for each process token, and then you have the security identifiers linked to each process, so which account or group owns the process. Then you can look through this example, which is to give you some inspiration on how far you can take this. And please, again, these exercises are actually really useful to do, so have a look at it. Okay, so we've gone through some table operations and some column operations. Now let's have a look at the selectors API, which is really a convenient way to select columns. So in order to use the selector API, you have to import it. So you have to do import ibis selectors as S. That's the convention to use. And then, we have the processes already loaded. So let's say you want to select all the numeric columns. then you can call this method in the selectors API, numeric, which generates a select statement that just returns all the numeric columns. So under the hood, what happens? Again, we can call to SQL to see what's going on. So what happens is that ibis somehow inspects the schema and notices that these are actually all numbers. So those are the ones we want to use to generate the SQL statement. Yeah, so there are a bunch of really useful column selectors. For example, if you want to select columns that contains a particular string or something like that, you can use select contains like this. It will generate a SQL statement that returns performs a select operation on all the columns containing ID. Sorry about that. It will use, it should be like this. So then you could do like it ends with a particular substring. You can do like a regular expression thing. So all of this is very, very useful. You can do multiple columns like this. Handles. So whoops, like this. So this will select just these two columns, but that you can negate it. So in effect, it selects all the columns that are not part of this list, like this. Back in the notebook, we're actually going through a fairly complex set of selector operations where we are loading the output from malfind like this, and then you notice that the malfind plugin has two columns, like the hex dump and the disassembly of the hex dump. These are large columns, so actually this is a good opportunity to look into the row viewer. So let's click here. You can see that this is really handy because it shows a lets us shows like these large column values in a more convenient format. So yeah, that was a bit of an aside. Let's get back to the selectors. Yeah, if you want to drop all the columns that contain byte data, so that would be this guy. You can do like this and this. So the effect of this is to drop the any column containing bytes data. Combining these two, we are effectively dropping both hex dump and disassembly, the disassembly column in this example. So in the following, we are doing a much more complicated operations, which I admit is perhaps more interesting if you're dealing with purely numerical data. But I encourage you to just read through it. And also the ibis project has this really, let's see, they have this blog post about maximizing productivity with selectors, which is useful to read if you want to do more data analysis. I want to just touch on something like how you would organize your projects. For example, how can we write reusable code when working with ibis operation? One way to do this is to introduce these utility functions. For example, if you had some functionality that you want to repeat often, in this case it's just a single operation, but let's say you often want to do some operations, you want to rename the columns to use snake case, so that's instead of you would instead of capital letters you would have underscores. Then you could create such a small utility function like this, and then you can also use the pipe operator to chain together multiple utility functions. So those would be functions that take a table expression as an argument and returns a new table expression. So for example, like this, you would take malfind, pipe, and the name of the function, this rename function. And then you could do like another pipe operation on the result like this. You had something like extract all the things. And this is how you can create really reusable code. So this is another example where we want to take this protection column, which contains information about the VAD. So if it's has execute or read write or whatever permissions applied. It's kind of verbose as it is now. So let's just rewrite this. So page execute underscore read write is RWX, page execute is X, and so on. So you can see here that we follow the same pattern in that we create an auxiliary function which takes a table expression T, and then we have a mutate operation where we basically look up the value, the column value in here, and then we map it to one of these guys. So here we do malifine pipe, first rename all the columns using the first function, and then we use another pipe and we do this operation, and you can see the resulting data set. Everything, all the columns are snake case, and we have successfully mutated these values. Now this is kind of interesting again to look at the SQL, like this query here will emit what SQL will emit. So this is just yeah, this is a lot, and yeah, that's one reason I personally don't like using SQL. I'm not sure if this is the optimal way to express this in SQL. I'm sure there's something more clever you can do, but I never learned how to do that. You can just do the same approach for column operations. To, let's say, we notice that we often parse the command line argument column, which is just a string, but we actually want to transform this into a list of arguments. So what we want to do is to perform this set of operations. We want to take the column, lowercase it, split it on white space, and then rename it. So this is how it's done. You define a new method, parse command line, that takes a column as an argument and returns a new column. And then you can see we use it like this on the command line argument data, select, then we pass the function and the column. And we also use here the deferred API, so that again really works well. So yeah, play around with this. Exercise 11. Like ibis is shipped with a lot of built-in functions, which, if you think about it, wraps existing functionality in DuckDB, Snowflake, and so on. However, there are sometimes functions built into DuckDB or Snowflake or whatever that ibis hasn't really wrapped yet. So in that case, if there's something that you notice is present in DuckDB which isn't exposed as a function in ibis, you can use this ibis UDF scaler built-in decorator to manually wrap it in ibis. So for example, yeah, there's some examples of functions. For example, base64, which is available in DuckDB, which isn't exposed in ibis. So what you have to do is basically use the decorator, then the name of the function, and then specify the arguments and return types, and then you can use it. So in this case, we are using the base64 function on the process column of the command line argument, the data. So you can see what you get back is the base64 encoded string. And you can do the similar trick here if you see with the if you need to wrap some aggregation function that hasn't been implemented yet in ibis, but that is present. It has to be present in DuckDB. Okay, so that was making existing DuckDB functions available that hadn't been wrapped yet by the ibis maintainers. But sometimes you actually want to write Python user-defined functions. So there you have another decorator, which is called this, that allows you to do so. Now, this actually happens in Python and not in DuckDB, which is implemented in C++. So there's some significant overhead in doing this. However, again, we are operating on a very small data set. So this is, for the most part, unproblematic. So let's illustrate how this works. So the malfind plugin actually has these two columns. It has the hex dump column, which is the row bytes, and then it has a corresponding column disassemble, which is the disassembled version of the row bytes. Now, let's assume that the disassemble column wasn't available and try to recreate the functionality using Python. So we would create a Python user-defined function using capstone to disassemble a byte string. So this is what we try to replicate. So okay, let's import some stuff from capstone that you can read about on your own time, and then this is the important part. So again, this decorator, and now we have a function. This is just a Python function which takes 2 arguments. So it takes code, which is some bytes, and then the offset, and returns a string. And then you have the capstone code here, which does this disassembly. And then you can see that, okay, let's do malfind. Let's do a selection operation where we turn only the disassembly column. So this is what the volatility produces. And then we have our own column, disassemble, which calls this function here on the hex dump data, and also on the address, the start of the address. Just we need the offset data. So here you can see that this actually works. You get the same output in both columns. So again, this is really powerful, and you're really fortunate that you're working with these small data sets that makes this feasible in practice. Together with what you learned in the previous notebook about Marimo, how the execution model works, how to create widgets, how to create visualizations and markdown cells and multiple columns and all of that, we have some really powerful tools for working with volatility data.